The options. All right, it's always technically challenging to get things figured out, but we get there on time too. Welcome everyone to the last GeoI seminar for the year. Amazingly, the year's been incredibly busy. We've had some great seminars, and I think it's a really good way to end off as well with Trimble coming in to talk to us about some of the work they do. We've been engaged with Trimble for a long time as a university and as the GeoI as well. Peter now sits on the GeoI board, so helps to give us some strategic thinking as part of that. And so he has kindly agreed to come and talk to us, and he's brought some colleagues with him, Dennis and Rob. I think I'll let you explain your various roles yourselves, but just let me welcome you. There's some food at the back for people who want to grab a coffee, and I'll hand over to Peter. Thank you very much. It's good to see everyone here and online.
Okay, thanks, Matt. I'm Peter Shaw from Trimble here in Christchurch. I'm an engineering director with Trimble, working in the geospatial sector. So that's we'll tell you a bit about the company in a bit, but that's about a quarter of our company, looking after field acquisition, reality capture, and then data processing deriving from that. Got two colleagues here with me today. Dennis Burney, who's another engineering director focusing on field hardware and software at the moment. And Dennis is going to present a bit of one of our local hardware and software innovation projects that's been very successful and very really significant achievement over the last couple of years. And Rob Lindors is a strategy director for Trimble Agriculture, who's going to talk about some AI-related work around doing more efficient application of fertilizers, weed killers. So it's all about sustainability, doing what we do in a geospatial sense more effectively and more sustainably. I'll start off with a little bit of a chat about Trimble itself, for those who don't know anything about the company. Won't go on for too long. We're not trying to do a sales pitch, just give you a sense of what we do and where we do it. We'd like to keep it informal. If you've got any questions during our presentations or at the end, we'll have time for that. So just yell out. So drive my slide deck. Here we go. So as I said, we'll start off with a bit of an intro to Trimble. We're a big company. We're about 13,000 people globally. We have a big presence here in Christchurch, about 400 people working off Birmingham Drive in Middleton. I'll give you a bit of overview of the company. I'll talk a wee bit about how we do R&D. So R&D in a commercial organisation is a bit different to perhaps how you view research in a university context. As I said, Dennis is going to talk about the digital antenna, big project that's been done here over the last several years. I'll talk about space weather and GNSS, how we get high accuracy in difficult space weather conditions. And then we'll do the ag sector AI stuff with Rob and questions at the end. So a real brief overview of Trimble. We started off in the mid-1980s as pretty much a hardware company that made GNSS receivers. There's a couple here that Dennis is going to talk about later, but they originally looked like big boxes that you could barely walk around with. Trimble started off as a spin-off, I think, from Hewlett-Packard when the founder, Charlie Trimble, saw the opportunity to take GPS technologies, which is pretty nascent there and originally a defence industry project, and saw the opportunity to apply that for civilian sort of peaceful applications. And that was basically the origin of the company in about 1985. By 1991, it had made significant advances in commercial and civilian applications of GPS, and started getting into markets like marine, actually also in 1991, they acquired a company called Datacom Software Research, which was the start of Trimble in New Zealand. It was a small company working, I don't know, somewhere in the centre of a city. Originally part of Datacom, which is the current New Zealand company, was spun out and sold to Trimble, doing handheld data collection with small computing devices. Trimble saw the opportunity to extend their market from merely position measurement to collection of data around that. And so they acquired us back there in 1991. 1994, we did the first commercial RTK system. RTK stands for real-time kinematic, but that's the significant step forward in accuracy for GPS measurement. That takes you from meters down to decimeters, down to centimeters with the right equipment. And so we started pioneering techniques to do that in the early and mid-90s. Then we started getting into other sectors, applying GPS outside geospatial into construction, grade control, machine control. And then we extended wider markets to take on optical scanning in about 2000. In fact, it's not here on the slide, but in 2000, we acquired a company called Spectra, which is a competing optical equipment company, and started augmenting GNSS measurements with optical-based measurements and terrestrial measurements. And since that point, we've really stepped outside that origin of a company into more working on enabling systems that utilize spatial data, allow it to be measured, modeled, and make decisions and make outcomes out of. So we see the business in three ways. We've got the where, which is the sensing stuff we've just talked about, the GPS receivers. Then you take that and run optimization algorithms on it, or your software on that, work out what you've got, what surfaces you've got, what objects you're measuring, all that sort of stuff. And then ultimately you're going to run sort of design processes on that to work out how to design a road, how to build a building, how to optimize an agricultural application or whatever. So what we've built in the modern Trimble, therefore, is a mixture of hardware-based, measurement-based capability plus software systems that utilize that data and then build them into wider capabilities. A bit in the middle there, and I'll point that out, the cloudy thing is something that my team here in Christchurch are involved with working on. That's what we're calling the common data environment, which is bringing together geospatial measurements of all types and allowing the customer to combine those and then more flexibly do what they want. So it's the direction our software is going in. Okay, so sectors, we started off firmly in geospatial. These days, about a quarter of our business is in construction. So that's working on infrastructure, building roads, bridges, water infrastructure. Our traditional GIS and geospatial backends, building digital models of the earth. So with scanning, photogrammetry, or just GNSS measurements. Transportation, we've got a large interest in transportation, so tracking the movements of fleets and optimizing the movement of typically commercial fleets, but also just private use vehicles to a limited extent, and agriculture, which Rob will talk about a bit in the past. So those are our four main sort of domains of application. A lot of data there, won't go through all those numbers, but between construction, geospatial, transportation, and ag, an awful amount of business is driven out of spatial measurements and the decisions that have to be made on top of those. Okay, final number slide. We'll get on to more interesting stuff soon. This is sort of around the financials of the company. We've now got about 13,000 employees globally. Most of those employees are engineers working on products and developing new technologies. Our earnings there, it's a big number, $970 million a year, of which, I can't see it here, but we spend about 500 million on research every year. So we're pouring back the revenue from the products we sell back into reinvestment and building better products each year. So it's we're a very engineering driven company. We're about the quality and effectiveness of our products. Says there, we've got R&D centers in 15 countries. I sort of went through the list and I wasn't quite sure I could figure out where all those were. But these are partial list of where we do stuff. In fact, that's the wrong way up. For the geospatial people among you, you recognise that that's sorted by latitude inversely. Christchurch at the top. So here in Christchurch we do GNSS as in hardware and software. We do machine control, we do field survey, we do some agriculture, we do quite a few things here. We've got quite a large and varied team. We've got a small team in Wellington that does what we call computational design. So that's around taking architectural processes, parameterizing those and making them repeatable and scalable. I won't go through the whole list, but you can see we've got a bunch of capabilities distributed all around the place. We've got expert groups of people with particular specialities, photogrammetry, inertial navigation, INS, that often supplements GNS to get accurate vehicle paths, used for autonomy and vehicle driving and steering, things like that. We've got a big investment in Northern Europe in particular, you see there in Espoo and Dandrid and Norway, design solutions. So we have a lot of capability around buildings design, bridge design, roading design that again links into the spatial aspects of measurement. How do we organize ourselves? It's difficult. We've got a lot of individual teams with point expertise across a lot of places. As our systems get more capable, they've got to link together. We've got to exchange data and combine capabilities. So our primary organizations are a customer-focused group of sort of domain organizations. So into our 4 main domains, which are geospatial, construction, transportation, and agriculture, or natural resources here, and then sort of more vertically focused groups in terms of looking at what the customer's doing, owner and public sector, so that's government, also education, and autonomy is around vehicle steering, vehicle driving. So we organise in terms of the customer groups and what those customers need to do. But then alongside that, we also organise in terms of underlying capabilities, what we call horizontal teams. So that's positioning teams who develop particular technologies that can be applied across those vertical groups. And then we have sort of expertise-based groups, we call them guilds or user groups, where engineers with particular capabilities get together and share knowledge and techniques and tool sets. So that's a really quick run through of, I guess, sort of engineering. Somewhere like Trimble, we try and organise ourselves across all of these distributed teams with some common tools and processes, and some of these are mandated things around cybersecurity and process. Some of them are just good engineering practice, which we slowly try to standardise over time. Yeah, it's a challenge. So what we're going to talk about today in more detail is sort of 3 case studies of research areas that we're working on. So I'm going to start off with Dennis's topic, which is around the design of a digital antenna, and that's around taking cost out and getting a really effective, affordable solution. So that's what it is. Thanks, Ben.
Righty-ho. Well, I'm Dennis Burney, as Peter said, currently looking after the field applications. I'll click right to the chase. I'll pass this around. I mean, the main reason I'll pass it around is just so you can get a close-up look at the Kiwi logo on there, the designed in New Zealand part. This is one of our prototype boards for our DA2 antenna. So, designed here in Christchurch. Actually, at the time, my team. I bought another couple of them actually cased up and all. But noticeably, one thing I didn't bring was one of our high-end survey receivers, because we don't have too many of those because they are very, very expensive. And that sort of leads us into low cost. One of the things that we challenge ourselves, Trimble in particular, is if we don't disrupt ourselves, somebody else will. So we don't sit on our laurels and just go, right, we've solved all the problems, this rake in money. We keep looking for new challenges, new solutions. And this is one of these. So we asked ourselves, what if instead of having a very expensive GPS receiver, it wasn't a CapEx, a capital expenditure for a business, a very significant cost? What if it was in another budget? What if, heaven forbid, GNSS was easy to use? And what if that could be available as a service when people wanted it? Now, one of the things, everybody loves looking at hardware and all, so we'll start with the hardware side of things about the designing and cost. So you're seeing the board being passed around there. It's as shown here on the screen. The tricks with GPS, right, is a GPS satellite, you know, there's a whole bunch of them circling the Earth. They're effectively sort of a 30 watt, the equivalent of like a 30 watt light bulb, 26,000 kilometers away. The signal that we're trying to track is way down in the noise. It's sort of mind-bending how you're able to find it, locate it, track it, and then get some information from it. But one of the ways that you can do that is by using specialized chips that are designed, built for that. They are expensive to make. So we took another angle, as you can sort of see if you look very closely at that board that's been passed around. There's no sort of specialized Trimble chips on there. It's generic processing, basically software defined. So we moved that out for as a cost reduction. We moved the compute off of the hardware in the first instance and ran our engine on the on Android devices as another way of lowering the cost of the hardware. Now it turns out actually that Android isn't really a compute platform, it's an advertising platform, and they're getting a bit more stroppy about people using their hardware for other things than advertising. So we've put some FPGA capabilities back onto the hardware and moved the engine back into the receivers. So this is the DA2 is a full-blown receiver. The other thing that we did was designed for manufacturing. So again, the piece that's been passed around there, basically no human hands have to touch that in the manufacturing process. Everything is machine placed. It's all run through soldering lines and multiple times. We've just driven down the cost as much as we could. For example, our high-end survey receivers can have $150 antennas on them, which have to be sort of hand assembled and finessed. The unit that we've been able to design is sub $10 actually, sub $5 for the first iteration. And also, as part of the whole system of things, and I'll come to this next, we took the cost and split it out so that you're buying a hardware which is capable of tracking GPS and giving a GPS position, but it's not giving you the full solution. And so that then becomes a subscription part of our solution. But that means the cost of this unit is low. This is a $500 receiver. It means that we have to make a unit that we can sell for that price and still make a little bit of money. Actually, that's a good question. $500. You've all probably got a cell phone in your pocket or hands that probably costs about the same, and it has GPS. But how good is the GPS on your phone? Huh? Not very? But how good do you think it is? Yeah, that's not actually too bad. It's 5 meters, 3.5 meters, that sort of realm. That's just, sorry? Yes, and it depends if you got the camera sort of up and facing anything interesting, and Google can start sort of pattern matching and doing smart things. It also, when you're on the street, it does smart things like going, if you're walking, you're probably not in the middle of the street, so it sort of hints and cheats a little bit there. But generally a smartphone is good for 5 meters, sort of 3.5 maybe. This receiver will get you below a centimeter accuracy when it's all up and going, and you've got all the options ticked. It can tell you exactly where you are. But doing that is hard, right? And probably the people we in the room here are the only people who perhaps the spherical trig, do they still do spherical trig at high school? Oh, they did when I did. we're the only people that sort of week of maths is applicable for, because we have to deal with a curved world and trying to present it on a flat screen or on a map. I don't think there's a whole bunch of different maps. Different people like their bit of the world mapped differently. Again, that's a whole bunch of projections and transformations right there. Its own unique sort of world of trouble and hurt and calculations. And then Peter's going to come back and touch on this, but then the world is a funny place and it does strange things. And I mean, that's one of the fun things working in, I guess, this space in GNSS. You get to go home and go, hey, so the plasma bubbles were playing up today. It's weird. And also other things, I mentioned the satellites, right? They're orbiting the Earth. They actually, Einstein comes into play with that, of course, because they're so far away from us in our gravity well that we have to account for relativity and the time difference, that time is going, I'll get this wrong, it's faster for them. And so the signals need to be adjusted. But anyway, a whole bunch of complication. The users don't actually care about any of that. You could tell them all about it, but what they want is that thing to very accurately, which is what they're paying for, tell them where they are. And then they want to get on with doing what they're doing. So our job is to just sort of fade into the background, quietly do our job and let the users get on with doing theirs. Right, so I mentioned subscriptions, and this is part of us trying to make things easy for people, because there are a whole bunch of dials and knobs and stuff that you can get in and tweak on these things. We've tried to simplify the offerings, and one of them is by just doing a fairly simple subscription thing. You can have no subscription. Here you go. This will give you 2 meters on its own for $500. You can go to our subscription systems, and this little diagram here depicts, you can pick your accuracy. We can give you 1 meter, half a meter, 30 centimeters, 1 centimeter type accuracy. The price also sort of goes up with that. Or you can go to third parties. Now, providing those services comes back to, as Peter was saying, Trimble is a very large organization and we're global. We have a global footprint. And we have a base network that spans the planet as well. We have stations on all the continents, all the interesting cities and everything. And we're monitoring the GPS satellites, the signals, the positions of those base stations, and that's where we're generating corrections. So globally, as you see in yellow, we can provide our RTX service. And again, that's either over the internet, or we can broadcast it over satellites. In the blue areas, we're providing VRS, which is the RTK, an older technology, but there are pluses and minuses to both of these things. But the real thing is to be able to provide, again, centimeter accuracy, you've got to have the guys who can figure out how to make the hardware, but you've got to have the ground network as well to gather the corrections and to know what to tell people, the little tweaks that need to be made to get the best out of these things. This is just a little bit of history. So we've, about a decade back, we sort of sat down and sort of looked at it and go, all right, Netflix has sort of proven that the subscription DVD business is working. So subscriptions are a viable business. We could look at doing this, at sort of carving out, instead of selling somebody a $25,000 receiver, sell them a $500 one, and then a $5,000 a year subscription to get the same level of accuracy. Actually, small digression. There was a problem with this versus a $25,000 receiver. How many times do you think they're going to let you drop a $25,000 receiver? Not very many. One of these, it costs us about $200 to make. And they're going to say, drop it. If it drops and breaks, and make it harder, drop it again. We dropped an awful number of these things, and they're solid. They survive drop after drop after drop. That I wouldn't want to do with a very high-end system. You know, the downside of winning, I guess. Yeah, technical details, numbers, and all this sort of thing. As I said, we started off with support on Android. Issues there with the compute and Google not wanting to share anymore. Also, there were a whole bunch of iOS users who felt left out. So moving it back on here and having a proper Bluetooth solution lets us work with the two major platforms. And here's another Kiwi sort of logo just to show off. The innovation is continuing where this is a next generation antenna that the team here in Christchurch are working on. And we just sort of have some fun with our prototypes and the ink screening on them. Sort of thought how far out we could push the boat with our manufacturers just to see what they'd let us do. And I think it played off quite nicely with that one. Righto, that's it. That's actually that is me. No questions? Yeah. Yep.
In the process, you're actually reducing capital value of the chip solution. Essentially, I mean, that presumably is largely an R&D cost rather than.
Yes, that is a question that is asked, but fundamentally, I mean, they're just different ways of implementing the algorithms. So that's the view that we've taken. One is we're implementing the solution through software, the other implementing it through fixed hardware. But with the DA2 I was holding there, that uses an FPGA, so that's a foot in both camps. Yeah, it's software, but it actually, you know, modifies the hardware on installation. So, good question. Oh, we had fun during the pandemic, yeah. Yeah, but that cuts both ways as well, right? If you're relying on a particular specialized chip, there are very few people who want that, so the volumes are lower. Equally, if you're relying on a very high demand chip or a high volume one, the demand can surge and all that, and you can be a little player in a big pond. Yeah. Yep. Sorry, you're going to come and take the microphone off now. Oh, sorry.
So it looks like sometimes there are other parts that bubble with things like energy solutions, etc. So how is this technology and is it you've shown that it's robust enough but yep. You know, things like if you were to install that kind of thing outside long term, is that a possibility, or it's really just designed for kind of traditional management?
Yeah, so it does come with a whole mount there, so it is primarily intended for user. What it's really intended is for that sort of light survey or GIS type work, and sort of just grabbing one of these and heading out the door and grabbing some points. It's not a marine antenna by any means, because you know, we've got a USB stick here, so that's going to corrode if you get salt on it. But it is weatherproof. It is actually, you know, it would be safe to leave out on, and you know, we have a number of these sitting up on our roof at work. So yeah, it is okay for a monitoring solution. And this is a USB cable. We're just using it for the power. So any USB power bank is what we need to run one of these.
In terms of things like storage, you know, if you work at store with someone really storage, is that a nice solution? Is that a possibility, or it's really just?
So this is primarily, I mean, what I'm talking about here is purely the hardware and the GPS, you know, providing positions. So I could go on I could go on a little longer about our field solutions and our different applications, which then gets into the data management side of things and into our cloud storage and such. But to an extent, we have our own solutions. Esri have their own solutions. There are various people where on the hardware side of here, this isn't a purely Trimble, a device for Trimble software. This is a device for Trimble users.
So Dennis, it's essentially updates the positioning engine in your device. And so whatever app you run on your device that has the data storage or what you're using it for uses that position rather than that position.
Yeah, that's a big other thing. So it's like if you had a station that had like an Android system, I'm sorry, not an Android, but Arduino or whatever system that was in, store it. So you need an external.
I don't know if,
to be able to talk to the device to be able to store the data if you were storing it. If you were
Yes. I mean, this will just tell you where it is, and broadcast that out. Something else has got to add the intelligence of, okay, why are we interested in that position? And all, but to your point about Arduinos and all, I don't know if our Spot has been here, but our Boston Dynamic Dog has one of these mounted on it for its positioning. So, and it's just talking to a Linux box.
Question as well.
Yeah.
I hesitate because I'm not sure the answer, but SBAS, stuff like baseball presentation system. It's been a big investment in Australia, similar systems elsewhere. How does that fit
in particular coming in now?
How does this affect business for this device, and what's your thoughts on that moving forward?
That's a very interesting question, and this is a very interesting location in the world at the moment to be, because South Pan is leading the way with the accuracy. Well, this supports the South Pan corrections, so
The current ones anyway.
and it also it's what is
dual frequency. I think it's
what is currently available. We know works on with this. Yes, and yes, those free solutions are a competition for some of our correction services on a regional basis as opposed to a global basis. And that again just comes back to a disruptor, right? And we had a good run with the global based business. The government funded solutions are getting better. That's a win for everybody.
Exactly right. So we'll support it, and it'll become more widely available. We sell RTX right now in direct. Well, it's not in competition with South Pan or what South Pan will deliver. It's more accurate than it at the moment, but South Pan will get to the point where it's strong and competing with it, which is fine. We will continue to support that, and there'll be different applications. I think the question that you made before about, well, what about our $12,000 receivers? Do we still make and sell those? That's right, we do, and they're used for different applications that can afford to pay for a better position. So that the R12, for instance, which is our premium receiver, that's sort of millimeter level accuracy. That gets augmented in all sorts of ways that we can't do in this. So we added an IMU, for example, for tilt sensing, and what else do we do on it? All sorts of other sort of augmentation devices that make that a more reliable, high accuracy, high availability signal for the person who wants to pay for it. But what we figure is there's loads of people who don't want to pay for that. We just want centimeters at the sort of price. Yeah, we can. We can. In fact, the Genesis team released.
Yep.
This
will do post processing. Yeah. And so, it's a subscription that you can, if you want to have post processing capability, we'll provide you the data. And since we're amongst friends, I mean, if you sit this on a tripod in the middle of the field, beside an R12, one of our top of the line survey receivers, you really have to tilt your head and squint to see the difference between them, right? It's when you it's when you want to get jiggy with it, that the tilt sensors and all this at the higher end receivers have come into their own and sort of give you more flexibility on how you use it, that you don't have to jump down into a drainage ditch or something to get the shot. You can just project the position down into it or into the tree or bush, other things. Multi-pathing as you go into foliage or something. Other, the higher end receivers have more capabilities than our lower end receivers. And that's just a spectrum in an offering. Righty-ho.
So we're going to flip and talk about one of the high-end solutions that the companies. Whoops, we went backwards.
Sorry, I went back.
Oh, there we go. Yeah, that's pretty cool. So we're going to talk about a different end of the problem, where again you're interested in very reliable, very high accuracy solutions, and you can afford to pay for them. So this is a research project that's been around. It had a lot of focus in Trimble the last 18 months in particular, and we'll talk about why that is. But it's to do with making sure that high accuracy GNSS works when there's bad space weather around. Now, I hope there's nobody here who's expert in space weather or atmospheric physics or anything like that, because I'm not. But I'll try and explain the problems we're trying to solve. So, as Dennis said, the constellations of GPS or GNSS satellites up there orbiting the Earth at around about 20,000 kilometers, spinning around outside with their little light bulbs emitting these tiny signals that we can pick up with the receivers. They travel through all these layers of the atmosphere. And the one we're going to focus on today, in particular in this sort of research project that we're talking about, is the ionosphere, which is there between, 80 kilometers and 10,000 kilometers. So as I'm sure you all know that basically GNSS works by timing the signals coming from the satellites to where your position on the ground is, and then doing what appears to be some pretty simple trigonometry to work out where you must be. Collateration is basically the technique. But of course, what's happening as the radio signals pass through the atmosphere is they get slowed down by what's ever in the way. And in particular, they get slowed down in the ionosphere by ionized particles. So that's usually a fairly dependable thing, and we build ionization models into the way the receiver algorithms work, and they can be differenced out in the way the way those equations work. But in some circumstances, things get worse. So sunspots. Sure, we've all heard of sunspots. They occur on something like an 11-year cycle. It's not quite regular, but they are flare-ups in solar activity on the surface of the sun that cause the emission of massive amounts of what's called this stuff, coronal mass ejection from the sun. That fields of photons that get, not photons, electrons that get thrown out in all sorts of directions. Some of them will end up traveling towards the Earth rather unpredictably. Some of them will hit our atmosphere, and they cause solar storms. So size of a solar storm on the surface of the sun versus the size of the Earth. These are big things. Luckily, the sun's a long way away, and we are largely protected from results of those. So sunspot cycles, solar cycles, have been observed for a long time. It's pretty impressive, really. That we're on what's called cycle 25 of these 11-year cycles. So they've been observed since around about the 1750s. There, people noticing odd things going on in the atmosphere or on the sun. So we're right here now. We're just coming up to the high point of cycle 25. Which is why we're interested in it, because as we get to it, it's causing some problems. It's a recurring but not entirely dependable. So there's lots of models out there that tell us when it's going to happen and how big these sunspot events are going to be. This one was predicted to be relatively small. This is the actual curve coming up. It's looking like being a bit bigger than was predicted. So that's going to cause more disruption over the next 6 months or so, and then it starts to wane. This sunspot cycle has about another 3 years to run before it declines a wee bit. Guy called Carrington back there in 1859 was the the first, I guess, formal scientists to observe these things. So the Carrington event caused disruption. And good old Wikipedia gives you a bit of background on this. What I love about this is that Carrington made a sketch of sunspots, and that sketch is part of the historic sort of scientific record recording these things. They're tremendously dynamic. So I wonder he got out his pencil quick enough to actually record this, but that's what a sunspot looked like on the 1st of September 1859 from wherever Carrington was sitting. Pretty impressive. So these coronal mass ejection things come flooding out from the sun. They get distorted by the Earth's atmospheric field, and some of that will come around and hit the Earth at the poles, but also in other parts. And when it gets there, it starts to disrupt the ionosphere and causes irregularities through the ionosphere, irregularities of electron mass. And changes in electron mass is a change in density of the matter that the radio beam's traveling through. So it's like light diffraction, or it is light diffraction. That causes scintillation, which is a high frequency change in results from the high frequency change in refractive index, and disrupts the signal coming from the satellite in different ways. So that by the time it gets to a receiver, you've got a much more messy signal than you used to have. This is what it looks like. This one, I think, is in this is a Northern Lights somewhere up in Norway, I believe. There's some great photos taken from the South Island recently that show similar things. This is what it looks like to the receiver. That's right. So what we've got there, RTK fixed is, so this is showing the accuracy of the solution that could come from a receiver like this. The times before the solar flare hits, you're down there at somewhere around what they 0.2 of a meter, so it was like about I don't know, maybe 44 centimeters or something like that. The moment the solar flare hits, then you lose the accuracy, and it flares up to something like a meter all over the place. The receiver's lost lock, it's lost the ability to count the number of radio cycles between itself and the satellite. So the cycle slip. So why is it a problem? It's a problem because if you need high accuracy and the momentary loss of high accuracy is going to cost you money, then you really need to fix it. So one of the areas that we've got into over the last couple of decades is autonomous devices, and some of our I guess highest paying customers are doing things like driving these massive dump trucks, earth moving machines around mines. This one's from somewhere in South America. You see on the top here is a couple of GNSS receivers. Those aren't VA2s. They will be getting making two independent measurements of the truck's position. That we're double checking each other, and the truck will stop if they stop agreeing. So they'll be supplemented by INS. That's inertial accelerometer measurements. Those two signals get out of lock, or get out of sync, stop agreeing, the truck stops. And that costs the mine site a lot of money. So a lot of pressure from the manufacturers who use this equipment of ours in these sorts of contexts to fix these problems quickly. A whole mine going down will be costing hundreds of thousands of dollars per hour. So what have we been doing about it? Sorry, this is another view of the same data. Normal signal, nice clear signal, rough signal during sunspot, all over the place. You can't maintain a lock and track on it. C to N is carrier to noise ratio. So the carrier is the portion of the signal that we count when we're counting the cycles between the receiver and the satellite. And it's a ratio of the strength of that signal to the random noise, and it goes crazy when you get a sunspot. So over the last 18 months or so, we've got receivers all over the place, all around the Earth. So we've been logging both raw observables, as I was talking about before, from receivers, and also logging in a few particular places, a couple of mine sites in South America, and another, I think it's a mine site in Keel Lake there in Canada. We've been logging the actual atmosphere, the radio spectrum at high detail. So we've picked up gigabytes of data of the radio spectrum changes during sunspot events over the last 18 months. And by combining that with the measured output from the satellites, or how we rather receive that output from the satellites on the ground, we can replay the scintillation events and see what would have happened if we'd had better algorithms running. So our receiver teams have been working on that stuff for a couple of years. There's a couple of nice aurora from Keel Lake in Canada. They've been looking to see whether they can characterize the change in signal, and these are what are called ionospheric phase scintillation measurements that show the presence of sunspots again. So we've developed algorithms that detect when this happens, when the signal is getting mushed up, and start to develop mitigation strategies for it. So I don't understand this, so I won't try and explain it to you. It's a lot of complicated mathematics. But basically what you're trying to do is pick out characteristics in the error signal that you can use to help solve the solution of a very noisy signal coming from a satellite. One of the things about GNSS is it's not simple trilateration. You haven't got 4 satellites that you can difference to give yourself a position. You've got 30, 60 satellites sometimes, or dozens of satellites up there that are within view of a quality receiver. So you've got lots of extra information, and you can use that extra information along with characteristics of how the noise behaves to figure out what's actually going on. So this is what our algorithm guys have been working on for the last 18 months. They've worked out up here how to characterize the behavior of the sunspot events, and they're doing it at 1 Hertz, so it's very, very fast. We've got a slower 60-second averaging going on to look at something called ionospheric gradient, which is more smooth measurement of the effect on the signal. The algorithms measure this at a known base station so that we can pull out the error coming from the scintillation event, and then we rebroadcast it over the CMR signal, which is what's used by RTX or RTK to correct a receiver station. So we've added in extra information to the CMR signal to improve the way that the fixing algorithm works on the end device. So the end result, I won't talk about fallback mode, is that here's some of this replay data that I talked about before. So the blue is a messed up solution with the horizontal error on the left-hand side. It goes out to about 17 centimeters. The 17 centimeters you can't steer a truck on. It's going to stop. It's going to wait. It's going to do no work. Lots of other things you can't do at that speed. So drop it down. You apply this what's called iono shield or iono guard. Actually, I think we have to change the name. You come down back into about a 2 centimeter, also yes, 2 centimeter position, all through those sunspot events. So we were pretty pleased with that result. It's just been released, and as you see, these events from back in September, and I think the firmware updates to enable this stuff to keep the trucks moving was released in October, early October. So that the wrinkles aren't out of it yet, but it's looking like a really effective way of keeping systems moving through these events. There's another shot of the blue being prior to the correction algorithms working, the yellow being post. Much better accuracy. A few other examples of that data. A few things still to do. We want to improve the way we gather this space information. It's not going to work in RTX fully. Lots of other work to do to make it work more reliably. Yeah, so that's an example of, I guess, it's the reverse case of what Dennis was describing, where we want to make the high accuracy available at a lower cost to a larger group of people. Here we've got people who are prepared to pay for a more expensive solution, but they needed to work all the time. They needed to work in all conditions. So with a whole bunch of work, they've managed to figure out how to do that. Any questions on that stuff?
So how many satellites does RTK use at a time?
It depends on how many channels it's got running on the receiver. A couple of dozen.
Depends on the base station. So, here, I think, I track 63 satellites for all the different constellations. So potentially, you can say, use all the constellations to put that base in those. Then your base is sending out corrections based on derived from those satellites. And it's that set of satellites that you roving around and then use to get a correct position. You out in the world depending on what the base is.
So the base station determines the number of any average.
It can vary. It's usually it's set up to use.
Very big range.
You're going to see around
20? Okay. So can it happen that sometimes the receiver loses contact with the satellite and the accuracy drops down? And how does it catch up if the accuracy drops down?
How does it catch up?
Yeah.
Well, it'll have to wait until more satellites come back into view with a usable high quality signal.
And that's where things like the R12 with the IMU come into play. Because then loses the sky completely, it's still got another sensor to go, well, I haven't moved, so I'm still probably where I was. And so that gives us some surety carrying on, continuing to output the same position.
So if it's connected to at least one satellite, in the worst case, then
The solution engine will continue. So if you're looking at a receiver and it's starting to lose satellites, you'll still see a position coming out of it. It'll start giving you a different metric, a different error metric on it. So you'll go from 2 centimeters out to 50 centimeters.
You always need 4 for a fixed solution, which in agriculture, I've been around for days. I remember when there was, we had to give farmers a model to say that this is the best time, especially if they were using vertical. That's 10 years ago. I don't think we ever have, we have sky plots and all sorts of things in our tool set, able to look at where they are positioned, the satellites are. Well, I don't think anyone ever has to use any of that stuff.
That's right. We used to do session planning and say, this time of the day, you'll be able to do accurate survey. But we don't do that anymore because there's too many satellites up there. You very seldom, unless you're in the canyon area, like a narrow view of the sky, then you've normally got more than enough satellites to get fixed.
You need 4 for a fix, right?
Or 3 for horizontal if you're really running it rough.
Someone always told me this.
And was that built in, a week out of measurement and it gives us an error?
Yep.
Is that practical? Or
Yes, yeah. No. Well, if you were looking at the HDOP and the PDOP, there's actually a better term for that now. I'm not sure what our current, what do we call horizontal accuracies these days? Still HDOP and PDOP? So our receivers anyway put out a error estimate with the solution all the time. If you're logging that and looking at that, so it will give you a scaled estimate of what we think the potential error in a given position is. So through past solar storm events, you would have been seeing an HDOP or PDOP value going up, which is giving you that. It's horizontal dilution of precision is the term. You'll see that value rising, and if it's getting outside your spec, then you know you've got a problem. But that value would have been accurate because it's reflecting the uncertainty in the solution. We just didn't know how to fix it before that. Yes.
And it's tackled in a number of ways, right? That's why satellites are multi-frequency. You have 2 signals traveling at different frequencies, they interact with that differently. So the receiver can determine, okay, now there's 2 signals that I know came from the same point source that have been altered on the journey. I can then sort of think, guess what's happening. And then the RTK solutions, again, you've got a base station in which there you're tying down where is that. So it knows absolutely where it is. And so then we look at the sky and go, okay, the error that I see has to be the sky. And it shares that. Right.
Okay, well, actually, we're going to swap over to.
I could go fast. Was it just arrow down? Okay, hi everyone, I'm Rob Lindors, work in the ag division at Trimble. I've been there about 20 years. And Peter kept using the truck example, but in reality, there's probably close to 1 million tractors out there today that farmers 100% rely on to steer themselves to get the job done. So for us and our business, like scintillation is a massive issue, because we've taught our farmers to rely on us to drive their tractors. Well, I mean, it's hands-free steering, turns around at the end of the field, puts the implement up and down. So no, they still sit in the cab, but they're not really controlling it. Yeah, back in the day, Dennis and I worked on the first ones. So what I wanted to talk to you about today was within ag, we're using some new techniques. Everyone talks about AI and the good, the bad, and the ugly of it, and so we're using it within Trimble Ag to do some really amazing things. And so I always like to start with the problem statements. The problem statement in the world today is weeds are becoming more resistant to chemicals. We as a population are becoming more conscious of what we put into our bodies, and but we need to grow more food. And so there's this kind of like polarization of things, and the technology today that we have can't get us to where we need to get to. And so there's like the Green Deal in Europe, for instance, sake is targeting 50% reduction in herbicides by 2030. That's actually impossible. Well, it's not possible because you can just stop doing that. But it's impossible to do that with the technology that we have today. We think we could get to like 13 to 15% if we did a whole lot of science around it. So how do you fix that? Selective spraying can do that. And so essentially what selective spraying is we go into the field with people all around the world with the jack pack, we call it. But essentially they'll walk the field at different times of the day, collect a lot of data, we annotate those images, and we train AI to look at specific species of plants. And then what we can do with that is we can drive across the field and only target those plants. Now, doesn't matter whether you use chemical herbicide or you use mechanical, it's still looking to find that plant. And the magnificent thing about that is it opens up all these different possibilities. So there's like biologics out there, which very, very expensive ways of treating or killing weeds, and 90% of farmers can't afford them. And so that we don't use them, but it's very safe and sustainable thing to do. There's chemicals out there that can't selective. So when we talk about herbicides or chemicals for killing weeds, there's really two types: of selective and there's non-selective. And so if you think about your lawn at home and you have clover in it and you spray it with what's called a selective herbicide, and it only targets those flat weeds, or those flat leaves, and it's just it all comes down to how the plant processes that or metabolizes that chemical. Well, some plants don't have selective herbicides, so you can only just target them with something that kills everything around it. And so really this is some of our studies, and we do a lot of work with this in Western Australia, farmers are saving up to 96%. So that's 96% less chemicals that we're putting on the food that we eat, which in the real world is actually a very good thing. And in the economic world, we think we can disrupt with this technology the chemical industry, just in herbicides alone, and cereal crops, and not even in all crops, by something like $3.5 billion a year. And so it's a massive saving for farmers, and it's a really good thing for our world. And one of the other things is, like, we never have any records, so we can actually go back in the year later, and some things, like I'll take wild oats, they sit in the ground for like 10 years before they germinate. Very, very hard to control, and so you actually know where the weeds don't move very far. You actually know where those infestations are, so you can actually do something about it before they come out of the ground. How does it work? Really, really simple. That's because I'm not an engineer and didn't have to build it, but we use a off-the-shelf camera. So it's just an RGB camera. Same as, it's about this big, same as what you can go and buy them off the shelf. It's the same kind of camera that's in your phone. We're using an NVIDIA processor, which you can go and buy, and off the shelf touchscreen display. We put a camera every 3 meters across the boom of a sprayer, and essentially that's its field of view. And for every 3 cameras, we have one of these processing modules. So it's capturing millions and millions of images, and it's scanning out in front of the sprayer and capturing those images and processing them, and then deciding what it should do. The kind of first thing that we do is we create this grid. So here's where the geospatial bit comes in, I guess, is we're actually calibrating a grid on the ground, and that's essentially breaking up this where the field of view is in the camera, and then it starts to capture the image. We go through, we run these things, and so we're running a 36 meter sprayer at 25 kilometers an hour through the field, and this is doing this real time down to a nozzle on a sprayer is 50 centimeters apart as a standard thing in the ag world. So it is smashing a lot of data very, very quickly to achieve this. And so it'll figure out what weeds are in what cells, and it can get down to the different species. We think the end goal here could be an inkjet printer, where we have 2 or 3 different ways that we're going to treat the weeds, and have different sprays coming out of different nozzles. But that's a bit futuristic. And then it transmit that and says, I need to spray that area, and it goes back and it tells the sprayer to just activate that one nozzle and spray those weeds. Some of the benefits, I kind of talked through that. We're kind of managing that resistance, which is a big problem in the world at the moment. But the real thing for us that makes me feel quite passionate about this is it's so much more sustainable and saves farmers millions of dollars a year. But if you can save up to 98% chemicals, then it's only good for all of us. And one of the kind of unintended consequences is when you spray a selective herbicide, even though some plants can metabolize it and some can't, it always affects the ones that can metabolize it. So you're actually damaging your crop It's just not damaging it as much as the weeds. So it actually gets us a better outcome and yield as well. I don't know whether I can get this to work, but this is just quickly should so you can just say in real time, it's just changing, it's just spraying, it's the jump here, that's spraying individual nozzles, rather than just what people would cut spraying, which is the general practice of the day. Looks way better on the screen here, sorry. Why is this super important to New Zealand? So we have like 1.7 million hectares of dairy pasture. Gets in the news pretty much every night for all the wrong reasons. But there is so much science out there that tells us how we can actually do it better. So there's this plantain, which if we mix it up with pasture, does lots of things around reducing the nitrogen and the urine, and therefore leaching, which we hear about. There's clover, which fixes nitrogen in the soil. There's all of these different things, but it's impossible to plant that in a single paddock and then control weeds like thistles and docks and different things like that. So this here is technology that can allow us to plant the right things and control the weeds at the same time. So I tried to catch up, how to go. And so this is just what an image looks like after we've been through it. So they go through every pixel and I do, you know, to train the model, and then for when we drive through the paddock, we can see that. So any questions?
Awesome, thank you. Really. Yeah. Slightly over, but that's okay. It's really fascinating stuff. If you, yeah, any last question or two? It's been good to have questions throughout, actually. I think it works really well.
I don't understand how that is. Do you need to protect the weeds first and then spread or it's all the protection and the happening next?
So kind of two answers. We have to train the model first, but the detection and the spraying is happening in real time. Does that make sense?
What's the accuracy? What's the accuracy to detect?
So we use the word efficacy. So it's we go out in the field and we put actual little flags on every weed, and then go across the field and check which weeds survived. Like 2 weeks later, you can't see instantly. And so, depending on the crop and the weed, we're seeing about, we won't release algorithm into the market unless it's over 85%. It's over 85%, 50%. And so we are, and that is down to like a 50% point. Like a couple of centimeters around. If it's we're looking for over 85% hit rate or kill rate before we release it. But we have to build an algorithm for every weed, every crop, and every growth stage. It's very exciting.
And the annotation training model, is that human?
Mm-hmm.
And how do you get to do that?
So well, there's two parts. So we have a AI engine that we run it through, because we collect billions of images that essentially is trained to go these 72,000 billion. We think you should take a look at just the industry and just interesting. And then we outsource some annotation, and then we have like the second annotation team that does checking. So yeah. there's lots of people, lots of people all around the world and different countries with different languages. Yeah, do that.
We are over time, so I'd have to kind of call it. I've seen a laser system as well. Have you?
There is,
Yeah.
that's what I kind of said, like the
It's expensive,
detection versus how you treat them. So we've gone after using conventional equipment.
Yeah.
Whereas there's people trying with AC current, DC current, like boiling, used vegetable oil. Like, there's all sorts of ways of actually going away, or even mechanical. Where I could see a time when there's they talk about the swarms of robots wandering around 24/7.
We needed a.
Not really sure how that's going to go.
Well, you can tell that obviously there's a lot of interest because we've run over time, which we try not to do, but it's always a good sign when we do. So please join me in thanking the team from Trimble for coming today and talking with us about some cool tech, geospatial tech. Thank you. And you guys are hanging around for a bit?
Yeah, we can hang around and take any more questions.